Okay, I'm going to start by looking at problem 6.20. All right, in this problem, there's a fluid that's being stirred by a rotating shaft. It has outer surface is covered with thick insulation, and the shaft imparts 50 kilojoules onto the fluid in the process. So energy is coming in, or in this case, work in the form of work. Um, or work is being done on the fluid, and we have a constant pressure and the piston moves outward. Okay. And let's see, they define that the energy is increasing by 20 kilojoules during the process. Okay. So this is a conservation of energy problem, right? So you have to account for all the energy. It's a closed system, right? So we're not having any like mass flowing in or out. Um, and it's perfect. So we have a thick layer of insulation, so we can make the assumption that there's no heat leaving this, okay, leaving this cylinder. And there's no information on here about any heat that's coming in, right? So there's only you're only doing shaft work inside of this. Um, and that shaft work, essentially, some portion of it is being done to perform work, which is expanding this or having the cylinder or the piston, sorry, not the cylinder, but the piston moving out to the right. Okay. And the work that's being done here is defined as boundary work. Okay. So let's take a look at how we might go about solving it. So we're just thinking about like the different components of this right now and kind of getting a general idea of what what the text means and how we can use that for us to solve this problem. Okay. So what are we trying to find here? Well, it says you're looking for the axial displacement. So basically, how far does that piston move out? Okay. What's given? The internal pressure is given, and it's constant. So that's going to be helpful for us, of course. If it wasn't constant, of course, we'd use this for the boundary work, and that would be a bit more complicated. Okay. Okay. So we also have a change in energy, internal energy in this system. Okay. And that's usually this is going to be to heat up whatever fluid is inside the system. That's going to be the change. So it's increasing, right? And then we have the shaft work that's being done on the fluid. Okay. So that's work's being done on the fluid. Okay. So here's our energy equation for a closed system. So there's no mass leaving in or out, no mass entering or leaving the system. So what do we have? Here's the difference between the heat. So heat in minus heat out. Okay. And then work in minus work out gives us the change in internal energy of that system. Okay. So it's like whatever's coming in minus whatever leaves, whatever's coming in minus whatever leaves. Okay. And the second part of this is that the second equation we have is the boundary work equation. Okay. And in this case, it's just the pressure times the volume at position 2 minus the volume at position 1. And I just wrote that as a delta, right? This is the change in volume, right? So it's pressure times change in volume is going to give you the work. Okay. Okay. So here's the solution that I took from the closed system equation. I'm going to start with that. That's this equation right here. And recognizing that there's no heat coming in, there's no heat going out. And basically we're following this idea that, it's thick insulation. So any heat that's leaving is negligible. Okay. So then the equation, of course, our closed system equation becomes work in minus work out. And that gives us our delta U, or change in internal energy. So I rewrote this equation, just bringing the delta U over to this side, work out over this side. And now we have work out by itself is equal to whatever's coming in minus the change. Okay. So it's already defined as 50 kjoules coming in of work being done and 20 kjoules of energy in terms of change in internal energy. So the work out is just going to be 30 kilojoules. Okay, so the next thing I did was from the boundary work equation, to say workout equals pressure times change in volume. All right, and then I rewrote it, wrote it as change in volume equals workout over pressure. And then I took the change in volume, just by definition for a cylinder, it's just pi r squared times x. So I define x as that, the essentially the length of the cylinder. All right. So just substitute in there for delta V, and then I divided both sides by, so I took this over here to the left, kind of skipped one step, put this on the left, and then I divided both sides by pi r squared, and then it shows up only on the right hand side. Okay, so now I have the displacement is work out times pi times my radius squared times the pressure. Okay, substitute in for those values and make sure you convert over to, for the radius, this is half of the diameter, make sure you convert over to meters, okay, because this is defined in meters, right? So this would cancel out, this would cancel out. Um, um, and you would, what it comes out to be, of course, is, you know, these meters cancel out these. So it would be a joule per Newton, right? And if you take the substitution and put joules as a Newton meter, what happens then, of course, then you're left, Newtons cancel out, and then the meters cancel out. I'm sorry, Newtons cancel out, and then you're left with just with meters, okay? So in order for the units to come out correctly, you need to substitute in for Newton meter for joule, okay? And then it comes out to be this.